The iPhone is one of the most complex consumer devices ever mass-produced. Inside a single smartphone are dozens of advanced materials, each selected for a precise physical, chemical, and electrical purpose. The outer frame is typically made from aerospace-grade aluminum or stainless steel. These metals are chosen for their strength-to-weight ratio, corrosion resistance, and ability to dissipate heat. Aluminum alloys used in smartphones are carefully engineered to remain rigid while allowing microscopic flexibility under stress. The front and back glass are not ordinary glass. They are chemically strengthened through an ion exchange process, where smaller sodium ions are replaced with larger potassium ions. This creates compressive stress on the surface, making the glass far more resistant to cracks and scratches. Inside the device, rare earth elements play a crucial role. Neodymium and dysprosium are used in powerful miniature magnets for speakers and vibration motors. Tantalum is used in capacitors because of its ability to store and release electrical energy efficiently in extremely small spaces. Silicon is the foundation of the iPhone's logic system. Ultra-pure silicon wafers are transformed into microprocessors using photolithography, where patterns smaller than a human virus are etched using ultraviolet light. Every material inside an iPhone is selected not only for performance, but for durability across years of heat cycles, electrical loads, and physical stress. At the heart of the iPhone is its System on a Chip, or SoC. This single component contains billions of transistors packed into an area smaller than a postage stamp. Each transistor acts as an electronic switch, turning on and off billions of times per second. Modern smartphone chips are manufactured using extreme ultraviolet lithography. This process requires vacuum chambers, atomic-level precision, and temperatures carefully controlled to fractions of a degree. The display is another technological achievement. OLED screens use organic compounds that emit light when electrically stimulated. Unlike traditional displays, each pixel generates its own light, allowing perfect blacks, lower power consumption, and faster response times. Beneath the display lies a complex layering of sensors, including touch detection grids, brightness regulators, and protective coatings that reduce fingerprints and glare. Power is supplied by a lithium-ion battery. Inside the battery, lithium ions move between a graphite anode and a metal oxide cathode. This controlled chemical reaction stores and releases energy thousands of times over the device's lifespan. Battery chemistry is carefully balanced to maximize energy density while preventing overheating, swelling, or degradation. The assembly of an iPhone takes place inside highly automated factories, designed for extreme precision. Before an iPhone leaves the factory, it undergoes extensive testing. Automated systems simulate years of use in minutes. Buttons are pressed thousands of times. Screens are tested for color accuracy, and antennas are checked across multiple frequencies. Thermal chambers expose devices to extreme temperatures, ensuring performance remains stable in both cold and heat. Acoustic tests measure speaker output and microphone sensitivity with laboratory precision. Software calibration is the final step. Each sensor, camera, and display is individually tuned to ensure consistent performance across millions of devices. The result is not just a smartphone, but a tightly integrated system of materials science, electrical engineering, chemistry, and industrial automation. The iPhone represents how modern manufacturing combines human skill with machine precision at a global scale. What appears to be a simple object in your hand is, in reality, the outcome of decades of scientific research and one of the most advanced production systems ever. Created one of the most advanced systems. Inside the iPhone is its camera module. Smartphone cameras rely on stacked sensor architecture. Light passes through multiple lens elements, made from precision-molded glass and polymers, each correcting distortion, color shift, and focus. The image sensor itself is composed of millions of photodiodes, etched onto a silicon substrate. Each photodiode converts incoming photons into electrical signals, which are then processed in real time. Modern sensors use backside illumination, allowing more light to reach each pixel. This dramatically improves low-light performance without increasing sensor size. Optical image stabilization systems use electromagnetic actuators that physically move the lens or sensor to counteract hand motion. These movements are measured in microns and occur hundreds of times per second. Additional sensors inside the iPhone include accelerometers, gyroscopes, proximity sensors, and barometers. These components rely on microelectromechanical systems, known as MEMS, where microscopic structures physically move in response to forces. Each sensor is individually calibrated during manufacturing to ensure accurate readings. Even minor deviations can affect navigation, photography, or user experience. The integration of these systems allows the iPhone to function not only as a communication device, but as a scientific instrument capable of measuring motion, orientation, and environmental conditions with high precision. Modern smartphone manufacturing also raises important environmental and engineering challenges. Extracting rare earth elements requires complex mining and refining processes. As a result, manufacturers increasingly rely on recycled materials recovered from old devices. Advanced disassembly robots can identify, separate, and recover valuable components such as cobalt, gold, and rare earth magnets with minimal waste. Future iPhone designs aim to reduce material usage while increasing performance. Engineers are developing thinner logic boards, more efficient chips, and batteries with higher energy density and longer lifespans. Research into solid-state batteries promises safer operation and faster charging by replacing liquid electrolytes with solid materials. At the same time, chip architecture continues to evolve. Smaller transistors reduce power consumption while increasing computational capability, enabling advanced artificial intelligence directly on the device. The evolution of the iPhone reflects a broader trend in modern engineering, combining physics, chemistry, automation, and software into a single integrated system. What began as a communication tool has become a compact supercomputer, manufactured at a scale of hundreds of millions of units, each built with astonishing precision. This is not just consumer electronics. This is industrial science in motion. Communication is one of the most complex functions. Inside the iPhone, multiple radio systems operate simultaneously, inside a space smaller than a credit card. These include cellular antennas, Wi-Fi, Bluetooth, GPS, and near-field communication systems. Each antenna is precisely shaped and positioned to operate at specific frequencies. Even a millimeter difference can affect signal strength and efficiency. This is why antenna design is tightly integrated into the phone's metal frame and internal structure. Radio frequency components must manage interference from dozens of sources. Shielding layers and grounding pads are carefully engineered to prevent signal loss and crosstalk between systems. The modem chip handles communication with cellular networks, converting digital data into radio waves that travel through the air at the speed of light. These signals bounce between towers, satellites, and devices thousands of times per second. To maintain stable connections, the iPhone constantly measures signal quality and dynamically switches frequencies, antennas, and power levels. This happens invisibly, without user awareness. This level of coordination requires precise timing, error correction, and power management. It is one of the reasons modern smartphones consume enormous engineering resources. Behind the scenes, what appears to be a simple phone call is, in reality, a highly synchronized exchange of electromagnetic signals, guided by advanced algorithms and hardware.
Ground control, confirm container alignment.
Alignment confirmed. Proceeding with lock sequence.
Where does this stack go?
Over by the 11 bays. Watch the corner.
Yes, I just arrived at the store now. I'll check the inventory and call you back shortly.
All right, that's scanned for you. If you just want to tap or insert your card right here.
It's finally happening. Look how close we are. I know, right? Are you going for the large one or the ultra? Here's your bag.
Thanks a lot.
Thanks a lot.